Okay, so welcome to the next session. My name is Jay Scully. This is session 2. I'd like to start off by introducing Wang, talking about median selection subset aggregation for parallel inference.
Thanks, Dee. Thanks, NIPS community, for giving me this chance. And thanks, everyone, for attending my talk today. So today, I'm going to talk about our recent work on the communication-free parallel feature selection for large-scale data sets. So here, large-scale data set, I particularly refer to the data set containing a lot of data points. This is a joint work with my advisor, David Johnson, and my friend Pei Chao. So large-scale inference often relies on distributed algorithms which store the data on multiple machines and process them in parallel. So typically, inference problem can be classified into 3 tasks. The first is feature model selection, the second is parameter estimation, and the third is prediction. So far, most of the work on parallel computing has been directed to the parameter estimation, either the traditional way or the communication-free, because this is always the most important thing we're looking at. However, I'd say feature selection or model selection is of equivalent importance because they are the basis for good parameter estimation. So for example, if you do computer vision, you want to select the best set of descriptors to characterize your images. Or if you do computational linguistics, you want to find the best embedding features or best topics to classify your document. However, despite the importance of the feature selection, not much work has been done in this track. So if we can design an algorithm that can do both parameter estimation and feature selection in parallel with minimum communication among machines, while at the same time maintaining almost the same level accuracy or even better accuracy compared to the algorithm running on the full data set, that would be awesome. And that's our primary focus of the paper and also my talk today. I hope that motivates you well. So my talk today is going to be organized as follows. I will first introduce the background of how people are currently dealing with a large-scale data set. And then I will describe in detail about our new framework. And then I'll mention a little bit of theory, followed by the numerical results. So let's begin with the background. So currently, there are 3 most standard ways for dealing with large data set. They're subsampling, stochastic optimization, and paralyzation. So I will not go into detail about the first 2 because they are not our primary focus here, but I will provide sort of kind of a basic concept here if you are interested to read. For paralyzation, I'm going to further divide it into 2 ways. Well, the first way is the traditional way of doing paralyzation. That is just parallelized sums. So let's look at a simple example. So for example, if you're doing a linear regression, and x, y are your coefficient, are the parameter, and as a data set, and you are going to find the coefficient that minimizes this object function. Now suppose you are using the gradient descending algorithm. That is, you are going to update your parameter according to this formula at each iteration. So in this formula, right in the red box is the gradient which consumes most of the time to compute. But fortunately, because of the independence of the data, this part can be decomposed into sums of different parts, where each part can be computed independently on each subset of data. So here's how it works. Suppose so this is a system, and you first attribute your subset of data into multiple machines. And at each iteration of the gradient descent algorithm, you first propose a new beta from the master machine, which will be passed to the submachines. And once you receive the beta in submachine, our machine is going to compute the part of the gradient with them, and then pass the value back to the master machine. Then after collecting these values in master machine, the machine is going to sum over to get the value of the gradient, and then propose a new beta according to the formula. And then it's going to next round and repeat until converge. So what's the problem of this system? The problem is that there is a huge amount of communication among machines, which might add extra burden into the system that weakens the reduction you gained from doing parallelization. So in order to avoid that, people propose a different way of parallelization. They call it embarrassingly parallel, but I say it's also communication-free parallel. So how we do this? Let's come back to the system. So it's the same as before. You put all your subset on the machines. Now this time, instead of asking them to work together, we ask them to work independently on their own. That is, you ask each machine to find their own solution to this linear regression problem. And next step, your master machine is going to collect all these solutions and directly combine them to get a final output. So in this system, the communication is limited to only the last step. So it's efficient. So the only problem is how can we combine these solutions to get a good estimate of the result. So one possible way is to do average, and that is in a 2012 paper by Zhang, Duch, and Wang. They prove that if you do this, your mean square error will be almost the same as if you run your algorithm on the full data set, which is very nice. So now, so far, it is all about parameter estimation. So for feature selection, we basically have two questions. The first is, how can we insert feature selection into this nice framework? And second is, how will it perform? Let's answer this question accordingly. So first, to insert feature selection into this framework, the first step is easy, right? So you just select your features on each subset. So you can say the first subset probably produce x1, x2, and x5 features. The second subset is x1, x2, and x3. So the real question is, how should we combine these different sets of features to a final one? So can we do average again? Probably not. You probably cannot average sets. So I think the most intuitive way here to combine sets is to do voting. So how to vote? So that's very simple. You just ask each subset to select their favorite features, then just scan over them and look at each feature, count how many subsets vote for them. And then you keep all the features that has at least half of total votes. So in this particular case, we will select features that have at least 2 votes. And we rule out the x3 and x4. And the final model will be x1, x2, and x5, and we refer to as median model in this case. Now with this voting scheme, we are able to describe our message framework here like this. So you first attribute your subset data onto all the machines, and you ask each machine to find their own set of features. This feature will going to be collected by the master machine, and then the master machine is going to vote to get the median model. After that, the median model will be passed back to the original sub-machines. And based on this model, all the machine is going to estimate the coefficient again, and this value will then be passed to the master machine and then averaged. This is the output from this system. And you can see this system is very efficient. The coefficient, so it's parallel, and the communication is only limited to 2 steps. One is for collecting all the models selected from subset, and the other is to collect all the coefficient selected from all the estimated from all the subset. So the next question is, how good will this system perform? And that leads to our theory section. So I'm not going to cover the whole theory here in case no one came to my poster tonight. But I'd like to highlight the most important and interesting part here. Hope that it will interest you. So although the whole system is adaptable to a lot of broader family of models, but here we only consider the simplest linear model for convenience. So again, let's assume the linear model, and we say we also assume the 2 case moments exist for the error. Okay, so for theory we need some conditions. So for the message framework itself, there's no extra condition we need. The only condition you need is a condition for your feature selection method to work. So in the paper, we are using Lasso. So here we have to assume the condition for Lasso to be held on the subset. If you are using a different feature selection method, you just need that condition to be held on your data set. Now with the condition for Lasso, the theorem 1 of our paper says that if your data set is partitioned randomly into m subsets, then the probability for you to select the correct feature will be increasing to 1 exponentially with the sample size. So this result is remarkable compared to the original Lasso result. So the original Lasso result says that if you run Lasso directly on the full data set under this setting, the probability for you to select the correct feature will converge to 1 only polynomially. So you're actually faster. So basically this says that if you using Lasso in the message framework, you are not only do the computation in parallel, which is faster, but you also have better result. You also have better model selection result, also the prediction result. So if you are interested in what's going on here, what's the magic behind, please do come to visit my poster tonight. Yeah, I will explain more detail about this at that time. So here we are going to verify this result in the numerical section and the experiment, in this section, we are going to compare a lot of methods and compare their performance. The methods we are going to compare in this section include the message we propose in this paper, and the median, where median here is also, we put it in the inversely parallel framework. You get an estimate on all subset, and then you take the median of the estimates to get your final estimate, so which is also very fast. But the last step is different. You just take the median directly of your estimates. The same, you have the average. You just take the mean of all the estimates you obtained on the subset. And we also have compared to the full set, where full set is you just run the algorithm directly on the full data set. Here we also compare to the bootstrap Lasso. So this is a little bit different. Bootstrap Lasso is, the procedure is you first bootstrap your data set to get a lot of bootstrap samples, the bootstrap sample has the same size of your original data set. And then you run Lasso independently on them and get a model, and then intersect the model to get your final model. And then the final model will be applied on the full data to get your final output. So model for comparison, we are looking at 2 regression problems. One is a linear regression, one is a logistic regression, and we use Lasso for feature selection. So the total number of features is fixed as 1,000, and we also fix the size of each subset to be 400, but allow the number of subset increase with the total sample size. For comparison of the performance, we look at 3 things. The first is the probability to select the true model, say the correct feature. So here, this is a picture for the linear regression with a normal error, and we set the coefficient. We set the correlation between the predicted to be 0. And here, from the picture, you can see both the median message and bootstrap Lasso are among the other 3 best methods. Well, they're all better than the Lasso run on the full data set, which is amazing. And second, we are also looking at the mean square error. That is, you use your estimated beta minus the true beta value and square it and see the result. So here, we can also see message and bootstrap Lasso are better than the full set data and are even better than the median and average method. And third, we are looking at the computation time. So because median, average, and message, and they're in the inversely parallel framework, and we fix the subset size. So the computation time for these 3 methods are constant, even with the increasing sample size. But the Lasso and but the full set and the bootstrap Lasso are increasing linearly with the sample size. That should be, right? So next, we're looking at the logistic regression, where if you look at the picture, because the computation time is almost the same as before, so we ignore that picture. So here, you can see the probability to select true model and the mean square error are even, the advantage are even significant compared before. So message, which is good and also fast. In addition to these synthetic data sets, we are also looking at some real data set from UCI data repository. So we look at two data sets. One is the power consumption data, which contain about 2 million samples. And another one is a Higgs classification data, which contain 10 million samples. So evaluation method we use is we're looking at the prediction error against runtime. It's like you run your algorithm for a while, and we stop, and we see how good your algorithm is going to predict for the test case. So for power consumption data, we use the first 2 million as the training samples and the rest as the testing cases. And we partition the data into 200 subsets. So the picture shows the prediction error versus runtime. So you can see all three, the message, median, and the average method are adapted down very quickly compared to a full data set because they are in parallel. But in order to compare these three, we enlarge the resolution on the later stage to see the clear position of the three. So you can see the message is even better than the other two. So here's the blue dashed line, if you can see. That is the result obtained by running the algorithm on the full data set until converge. So you can see the message algorithm actually adapted to that bound very, very quickly. It's almost the same. So like you just take a little time for you to get to that place. So for Higgs classification data, we are using the first 10 million as the training samples and the rest as testing cases. And we partition the data into 1,000 subsets. So the same, if you look at the picture, you can see the message and all the three are better than the full data inference, but message is definitely better than the two. We also enlarge the resolution for you to have a more clear impression here. So you can see now in this case, message is even above the blue dashed line, which means that even you run the algorithm on the full data set until converge, message will still be better in terms of the prediction error. Great. Okay, so here we propose our new parallel framework for both parameter estimation and feature selection. It can speed up your computation, the parallel framework, and it can also boost the feature selection accuracy and prediction accuracy. So this is kind of a double gain for using this framework. The implementation is very simple. You just need to divide and vote. And the conditions can be satisfied by many datasets because the message framework itself doesn't require any condition for you to use. And it's also easy to generalize. So, and you're done. Thank you.
Okay, we have time for one question. Yeah, we'll repeat it here.
Okay. So the question is, looks like the main advantage is the model selection accuracy is very good.
Yes.
And I'm just wondering, so if the model is selected correctly, you can always do another least square to get the accurate prediction accuracy.
Yes. Yes.
So here, look like you haven't done that.
So could you repeat the question before answering, please?
Sorry. So the question is, if model selection is better, you can do estimation better. Is that your question? I think that's what we did. You mean, so based on the selection to the estimation, that would be better, right? And actually, that's what we did in the simulation, all the thing we did. So we select the model first, and based on the model, we do the prediction. So that's why it's better than the original result. Here for lambda, we use the extended BIC. If you know, there's a paper in 2008 where.
Okay, I think we're going to take it offline from here.
Okay, sorry, we can discuss later.
So thank you again.
Thank you.